Hello everyone, this is a video lecture for Calculus 2, Section 8.1, arc length. Let me give you a formula. So the formula for arc length that we're going to be using all today is S is equal to, that's a little s, is equal to the integral from a to b of the square root of 1 plus f prime of x all squared dx. This is something that you'll be using in this class, of course, and in Calculus 3 in particular, because this is Calculus 2 now. So when you move on to Calculus 3, you'll be using it there as well. This formula comes up a lot of different places, so just as you go through the rest of the class, you'll be seeing stuff like, ooh, I think I've seen that before. And yeah, it's just arc length is all it is. And there's variations to this as well. What is an arc length? Well, let's just start right quick with a flat line. And I'm going to go from 0 to 5, and I want to know what is the length of that line right there. What is that arc length right there? It's 5. Yeah, exactly. 0 to 5, it's 5. So that's easy. Okay, so what if I had like a line, a straight line here from 0 to 5? Can you find the length of that guy? Yeah, it's Pythagorean theorem essentially, right? Because you can see that there's a triangle going on there. Okay, cool. What if you have this kind of line, and they say find the arc length from 0 to 5? And so, it's not exactly straight. You could probably approximate it, but to find the exact value, you're going to have to do some calculus. Okay. One other thing that we've seen arc length before, let's say I have a circle, and I want to know what's the arc length of this guy right here from 0 to pi over 2. Well, that's a special formula for arc length stuff. S equals r theta. We saw that way back in college algebra, I think. But this is not what we're talking about here. That's nifty, but we're really trying to focus on this kind of stuff, okay? So let's just jump in. 81001. So I've got y is equal to 3 minus 4x. They want to go from negative 2 to positive 3. It says find the arc length. My S's don't look very good. There we go. I have a little note here. It says, well, it's a line. Yeah, isn't it a line? Look at this. This is a line. And so I'm going to actually just use Pythagorean theorem, and it's going to be funny. So there you go. I'm going to plug in the negative 2 right here to see what we get. So x1 is negative 2. So y1, when I plug that in, I get 3 minus 4 times the negative 2. Positive 8 plus the 3 makes the 11. And then I have x is equal to 3. When I plug in the 3 over here, my x2 is going to be 3 minus 4 times 3. That's 12. Negative 12 plus the 3 is going to be a negative 9. And so I've got 2 points here, negative 2 comma 11. And then I've got 3 comma negative 9. And I want to find the distance between them. And so that's going to be the Pythagorean theorem stuff. So negative 2 minus the 3 all squared, 11 plus the 9 squared, 2 negatives make a positive, and blah, 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 we get 5 squared plus 20 squared, the square root of 425, which ends up being 5 square root of 17. Cool. That's your answer. You're done. There's nothing else to do here. What I want to do is use this, though, as a good example problem for what we're going to do with any problem. So this is a pretty simple one to start with. And so what I want to do is follow that formula of 1 plus y prime squared. Notice that I simplified it a little bit, and that's what we're going to be doing to make it much easier as we keep going. So I have 3 minus 4x here. So when I take the derivative, I got a negative 4 dx, blah, blah, blah. I just want y and y prime. Just make it easy. Just keep it easy, okay? So my real integral is going to be negative 2 to 3 of the square root of 1 plus negative 4 squared dx. Again, we're going from negative 2 to 3. So yeah, just verifying there. Well, here we got 4 squared, which will make a 16, plus 1 will make a 17, right? Dx. And to make it funny, you could technically move that square root 17 to the front. Now it's integral of 1. which means that you just put an x in there. I messed it up. You see I flipped them? 3, 2, 2, 3. Nah, dyslexia, it hits us all. So, or at least it hits me. And so I get this guy here. 2 negatives make a positive again. 5 square root of 17, and there's your answer. Cool. Okay. Let's actually do, like, I don't know, a harder problem. 0, 0, 9. So I got y is equal to 2/3 x to the 3/2, and I'm wanting to go from 0 to 1. Find the arc length. So in order to do this arc length, of course, here, I want to find a derivative. And so let's go and do that on the side first. And so I'm going to say bring the power down. Well, the 3/2 and the 2/3 actually just all cancels out, and you subtract 1 from the power. There's no chain rule or anything. So we got basically the square root of x. And so I'm going to plug that in. I've got 1 plus the square root of x squared. Well, square root and square cancel one another. Leave me with just this guy here. From 0 to 1, of course. And so don't overthink this. This is actually a 1 in the front, so there's not really a chain rule going on or any kind of u substitution needed. This is all to the 1/2 power, so I'm going to add 1 to the power and divide by that new power from 0 to 1. Obviously, the front is the 2/3. Now to the 3/2 power. Plugging in the 1, we get 2. So 2 to the 3/2. I don't think there's any kind of simplifying for that. And then when you plug in a 0, you still get a 1. 1 to any power is still 1. I guess you could, I don't know, do something like a factory kind of thing like this. I don't know. That's what I have. It's good enough. Keep moving. 81014. Yes, that's a 4. X is equal to y to the 4th over 8 plus 1 over 4y squared, and we're going from 1 to 3. So I want you, as the student here, to pay attention to this problem. This is a very special problem, and you'll be seeing this problem multiple times in this section alone, if not later on. So there's something about the powers and stuff here and the numbers that just makes this problem different. And that's okay. It looks kind of standard to us right now. Let me just do the derivative, and I'll show you why actually. So that's my x. I'm doing it in terms of y. Don't let that be confusing to you. It's just x prime now. Dy, whatever. It doesn't really matter. Just as long as you're taking the derivative of this guy and you're going to plug it in. That's the main thing. So that's what I want to do. I want to take the derivative of this guy. So I got my 1/8. Again, my derivative means the 4 is going to come down to the front, and now I got a cube. Over here on this side, though, this is technically a 1/4 y to the -2 because he's in the denominator. And so when I bring down my new power here, I get a -1/2 now. This guy's going to be a half here in a second, too. Y, and then again, I'm subtracting 1 from the power to make a -3. Let me make this a little bit more clear to you here. And this right here, this right here, this is what you should take a mental note of, okay? Kind of like take a snapshot in your brain of what you see, because we're going to be seeing this here in just a second again, okay? So this is an important milestone, and that's good. Okay, so I'm going to plug this thing in. I'm not really going to think too much about it. 1 to 3, was it? Yeah, 1 to 3, square root of 1 plus all this stuff here, squared, and the square root of that, and then dx. Oh my. How do I even get started on that? So I want to simplify, actually not just that, but this with the square. And so a square means that we have 2 of them simultaneously. And I'm going to just do this so that it's a little bit, it's not really, I would say, more user-friendly, but maybe a bit more user-friendly. There's 2 of them. That's what the square means. And what I want to do here is I want to simplify. And in particular, what that means here is that I want to FOIL. Okay, so foiling means I'm going to multiply this and that and all this stuff here and see what we get. So this one times this one, I get 1/4 y to the 6. Again, I'm multiplying their bases, so I add their powers. 3 plus 3 makes a 6. When I go over here, I actually have the 1/2 and a negative 1/2 to make a negative 1/4. You'll be seeing that throughout all of these. But notice that I have a positive 3 and I got a negative 3. And so I'm saying positive 3 minus 3 makes a 0 power. A 0 power is simply a 1 in the front. And the same goes for this guy here. Okay, so I'm going to get that 1 right there. And then finally, over here, 2 negatives make a positive, 1/4, and then y to the negative 6. Now, again, we could put in the denominator if you like, but either way. These do not cancel. They actually combine. And so I'm going to rewrite this one more time here. Like this. Again, this should be some mental notes for you, okay? This is a good thing. If you see this, we're going in a good direction. Let's go back. So this was the simplified inside with that square root kind of stuff. Well, there was still a 1 plus. And then all this stuff. And I know that it doesn't look any better right now, but again, there's a special problem, and I'm trying to show you how to do this very particular problem. These here are both constants, and so they combine together. And what we get is a 1/4 y to the 6 now plus the 1/2 plus the 1/4 y to the negative 6. Okay, pause, 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 pause. This inside here looks very interesting. Doesn't it look very similar to this guy right here? Don't these look almost the same? What's the only difference? Is that the sign right here. That's the only difference. And so here's my thing is if they're looking very similar, I can actually reverse the process. Okay? I can actually take what I had. Instead of having a minus, have a plus. Well, how did I get that minus? Because both of those were negative. So if I make both of those pluses, that means both of these were pluses, and that means that this guy was a plus. And so what you actually end up with at the very end is something very, very, very similar to what you had started with, okay? I'm going to write it out the long ways just this once so you could see it. Plus on the inside. And again, that was the square. Notice right here. Take a mental screenshot of this, a mental picture. And let's go back up for a second, right here to this guy. Half y cubed. Negative half y to the negative 3. Half y cubed plus 1/2 y to negative 3. So what I want to show you, I guess, through this is that when you see this problem here, and you see this particular style with the 1 plus, what you can do is skip all this. You can skip all this. And you can basically just end up with this guy. You say, you know what? There's a 1 plus on the outside, and there's a negative here. What's going to happen is that this guy's going to change to a plus sign, and then that's it. You're done. Like, that's it. You're done. And so that's what I'm going to do now. Notice that the 1 came inside and made it a plus. But again, that's way oversimplifying what I just did. Look at all the steps I had to do to get there, right? So there's no way I could just say that's a legal move, but I've tested and proved it. I've done it myself now. Notice that the square and the square root will actually cancel, and that's actually the point of this problem, is that everything simplifies down to something that's much, much more manageable than what was first thought. Notice the square and square root are gone. That's it. This is your integral, and we're going from 1 to 3. Okay. And so I actually just integrate now, and that's not too bad. So I'm going to add 1 to the power, divide by the new power. I'm going to add 1 to the power and divide by the new power. Doesn't this look very familiar to the very first original one that we had? Hold up. Didn't I have a 4 and a negative 2? I mean, very, very beginning. A 4 and a negative 2? Wow. Do I get an 8 and a 4 just like last time, though? Actually, I do. Yeah, I actually do. I'm going to have an 8 and a 4. Just kind of silly how that all works. I don't know if I would stress that similarity, I would stress this similarity. I wouldn't just say, oh, well, the answer is obviously this. Doing one or two little steps might change the inside numbers. I'm not going to assume that they're just always the same, okay? So it just so happens to be friendly this time. I'm taking this from 1 to 3, and I should be able to simply just plug those guys in. So I got a 3 to the 4th, and here I got a negative 1/4, 3 to the negative 2, and then all this stuff here, I'm going to say minus, and then I'm going to do it all over again with the 1, like that. You do the math, and this is definitely calculator, and 1 to any power is just itself. It's just 1 and all that kind of stuff. So 92 over 9 is what you end up with a calculator. That's a good way of using calculator, by the way. No need to do all that stuff by hand, okay? Cool. So that's a classic problem, and I said that you would see that again, and that is correct with this number. I actually have nothing on this question. I don't even have the question written down on my notes. All I have is that this is the same thing. Okay? The same trick. I actually have that written down. It's the same trick. And so when you get to that problem on your homework, repeat. Okay, next problem. So I've got now y is equal to ln of secant of x. And we're going from 0 to pi over 3. Okay. And of course, just like last time and every time, find the arc length. So I want to find my derivative of this guy. Derivative of ln is 1 over stuff. I know you probably already got the answer. Chain rule, derivative of secant is secant tangent. And then actually that's it. So the secants cancel. And so your derivative is just simply a tangent. So like what's the integral of tangent is ln secant, right? So that's just a formula we've seen before already. I'm going from 0 to pi over 3 of the square root of 1 plus tangent x all squared dx. Well, this 1 plus tangent squared is actually kind of interesting because if you use that Pythagorean identity, something like that, this cancels, or doesn't cancel, it creates a secant squared. So those are identical. And you can cancel the square root and square, making it even easier. And then, hey, what's the integral of secant? We've seen this before. It is ln of secant plus tangent. Okay. This has come up enough right here that you should probably write that one down. Just saying. Because I've seen it enough just through these recordings that I've memorized it, again, I guess you can say. Cool. So I'm going to plug the stuff in, of course. Ln secant pi over 3 tangent pi over 3 minus ln of secant 0 tangent 0. Well, tangent 0 is 0. Secant 0, I believe, is a 1, but ln of 1 is 0, so that goes away. Tangent of pi over 3, sorry, it doesn't look very good. It kind of looks like a 6. Tangent of pi over 3, so pi over 3 is the bigger one. Y over x, rise over run, slope, that's my tangent. I would get a square root 3 over 2 over half, so I think this just ends up being square root 3. My cosine at pi over 3 is the smaller version of 1/2 because it's secant. I flip it to make a 2, and then I got my ln, and well, that's it. You do not need absolute value signs because the inside number is already positive. I just left them because whatever. All right, 8, 1, 0, 2, 5. So I have y is equal to 1/2 x squared. And they give me 2 points. They say negative 3 comma 9 halves. And then I've got a q 3 comma 9 halves. And what they're wanting is the arc length from this point to that point. And I just want to be clear, this derivative is super easy. The 2 comes down, cancels with the half, and you get an x. And so it's literally my integral of the square root of 1 plus x squared dx. Now, here's the thing. actually, you can also just look at your x values and just plug those in too. So you're good here. And to me, it looks easy enough that, I mean, heck, shouldn't I just be able to figure that one out, right? Well, no. If there was an x here, then yes, it would be a simple u substitution and it would be easy. But that does not work in this case. What I tried first was creating a triangle, and I went through all the trig substitution stuff, and it was just a nightmare. And I just stopped. I actually crossed through all that on my notes. Like, I mean, I wish I could just take a snapshot and show you what it looks like. It just looks like junk. And eventually I just said, hey, just use a formula. Just use a formula number 26, apparently. At least my number 26. 1/2 x square root of x squared plus 1 plus ln of x plus the square root of x squared plus 1. And then again, all this from -3 to 3. Can you see why I eventually ended up using a formula? I mean, look at that thing. This was unsuspecting. I'm like, yeah, I like this guy. And then I actually see the result, and I'm like, not really. So what steps would you have taken to go from here to there? Exactly. That's my point. It would take forever. So it wasn't so easy. I plugged these guys in. I didn't even show that in my notes. I just got the answer. It's pretty simple stuff here. ln 3 square root of 10. There you go. So good to go there. Next question. So I need to talk to you about this problem. It's a strange one. So they say use Simpson's rule. N equals 10. So that's approximation, by the way. To find the arc length of y is equal to x times the sine of x. And I'm going from 0 to 2 pi. Okay. So we're supposed to find out this this arc length thing. So first off, I need to take a derivative. And so y prime is equal to, here I've got chain rule. I'm sorry, product rule. So I got a 1 and a sine x. Leave the first one alone. Sine goes to cosine. And that's really not any better, by the way. Not that this is complicated right now. But my problem is that this guy is going to go on the inside of this integral. 1 plus the sine x cosine x stuff all squared dx. I mean, look at that. It's not exactly easy. And I actually have in my notes, it says you can't do this normally. And so therefore we are using Simpsons. So how do we use Simpsons with this particular problem? I apparently left off a square root at some point, and I don't know why. My notes just don't have a square root, and that's kind of puzzling to me. It should include the square root. The whole entire function here, this thing on the inside, this is what we're going to be using for my Simpsons stuff. My delta x... Ugh. My delta x is the pi, or 2 pi minus 0 over 10. And so we're going to put a pi over 5 all over the place here. What I'm getting at is that we start here at 0 and we're going all the way to 2 pi. And they're wanting 10 subintervals. And so I have to cut this up into 10 different places. And so it's actually every pi over 5. And so that would be a 2 pi over 5. And then 3 pi over 5, and so on and so forth. Not to scale. 2 pi would actually be way over here somewhere. So we're going to be using these numbers here, 0, pi over 5, 2 pi over 5, etc., all the way down for our Simpsons rule. 2 pi minus 0 all over 3 times the 10 times, and here we go. I've got f of 0 plus, again, 4 f of pi over 5 plus 2 f of 2 pi over 5 plus 4 times f of 3 pi over 5, 4, 2, 4, 2, 4, 2, 4, 2, 1, and then you're done. Well, guess what I used? Yes, I used Excel. That's right. I used Excel to get this answer, just like we did back in the Simpsons approximation section, whatever. And I got this answer, and that was no problem at all. Good to go. Walk away. Okay, so I'm not going to go back through that. You can go back and find that in the previous sections. We already did that once. Okay, cool. So I used Excel, and I got that answer. Great. And then, this is where we got to talk, and then they want you to use a graphing calculator. What do they mean by that? Use a graphing calculator? I'm going to go ahead and give you the answer that they have, which I have also found, but we'll have to discuss it. 3746. Okay. And that was it. Apparently 4 decimals is good enough for them. This is very similar to this. We should get 14 and a, or 15 and a half, right? That's the answer. But obviously they're off by a little bit because this right here is an approximation. And I don't want to use exact. I just want to say more exact-ish. Because it's not exact. Exact would be like square root of blah, blah, ln of blah, or whatever it is. No clue what the answer is. That's not the point. They want a decimal answer, so it's not really exact, but it's the answer. This is the answer, and this is just an approximation, okay? And they're different enough that WebAssign is not going to allow you to just put in the 1 twice and call it a day, okay? So you actually have to do something about this with a graphing calculator. I recommend Wolfram Alpha. Wolfram Alpha. I'm not going to show that right here. I think that this program's a very strong program. If you go to Wolfram Alpha, you type in this integral in English, and you hit enter and it solves it for you. It'll do all the math for you. It's super awesome. It's also not allowed on tests. So it's okay right now because, again, the questions that they're using here are on the homework. And they're expecting you to kind of try to use different methods of solving these things. So don't think, oh no, I'm using Wolfram Alpha here, but you can't use it on the exam, and what am I going to do? You just don't use Wolfram Alpha on the exam because they're not going to have these kind of questions on the exam, okay? It's going to be okay. Don't fret about it. Just let it go. Sometimes just, there's, new stuff out there. And, of course, there's tons more applications that solve integrals for you like this. I'm just listing one that I commonly go to that I kind of like myself. Okay? Again, I'm not going to show you. It's just pointing out different tools. You can at least, here, just between you and me, you can at least use Wolfram Alpha to double-check your answers on the homework, right? So, like, if you got some crazy integral or something, you don't know if it's going to work, just, I don't know, type it into Wolfram Alpha and see what they get. If it's different, and it probably is, it might be just a simplification problem. I don't know. Just a different way of seeing it, okay? Just tools, not crutches. They're tools. So we got 2x to the 3/2 power, and they have p naught. P naught, that's a little 0 down there, by the way. This is my starting place. That does not look like start. This is where I'm starting. And they say find, this is a strange problem, find s in terms of x. They want the arc length as a function in terms of x from the starting point. This is a weird problem. I actually wrote that in my notes. It's a weird problem. So I've got my integral from 1 to x of 1 plus 2. Why did I put a 3 there all of a sudden? Oh, okay, I know why. Let's do y prime and then dx. Yeah, no, squared. Yeah, no. This is not correct. There is a small piece that is no good. You're using an x here because of this x here, which I'll explain here in a second. This x does not belong anymore. In fact, this x right here does not belong anymore. You can't use x. So what we're going to do instead is use a t. Okay? Now, why? Why is all this going on? Why are you changing my whole world around? What's going on? Think of it like this. I have a starting point, p naught, and then I've got this crazy little function thingy that does this. Right here. This looks nothing like this. Nothing at all. But the point is that we're having to use calculus. I can't just make a straight line and use Pythagorean theorem or something like that. But what if my x was right here? What if my x was right here? What if it was way over here? What if it was way over here? I want to find a function that'll give me the full arc length up to that point. Okay? So I just simply say, well, where's my ending point? Right there. And it gives me the exact answer by just plugging it in. Okay? That's the goal here. So I can't use x all over the place. I'm going to use t instead here, and t right here as well, so that I can differentiate it between what they want as the answer. Okay. So I still need my derivative squared, and then again dt. So my y is now not 2x, it's 2t to the 3/2. So my y prime, again, the 3/2 comes down, the 2's cancel, leaves a 3t to the 1/2. That's a square root, but we'll deal with that here in a second. Square both of those terms. I guess you can kind of say, like, distribute the square, though that is a little bit strange sometimes. Here in Calculus 2, you're fine. So just 9t, 3 squared, square root of square, a square root of a square root. The square root of a square. They cancel, make a regular 1t. Okay, cool. Again, notice that we have a 9 here in the front. So when I integrate, I'm actually going to get a 1/9 in the front here. This is a 1/2 power. I'm going to add 1 to the power and divide by the new power. That's the u substitution stuff that I just didn't care to do. From 1 to x. This 2 can come up, the 3 can combine, and so we get, what, 2 over 27, I believe? 9, and then this is where it gets a little bit weird. Plug in the x to get an x. And then I plug in the 1 to get a 10. And that's actually your answer. It's a function in terms of x. That's it. That's it. Just don't do anything else. You're done. Type that in. You're good. Okay. I have another note here. It says that the rest of the stuff in the section all use graphing calculator. So just go back and do some Wolfram Alpha once in a while. I know there's other tools out there, but that's the one I guess you could say, recommending. Other than that, that's all I got. Thank you very much. Have a great day.